So it's my great pleasure to introduce Dr. Sakura Pascarelli. Sakura received her PhD in physics from the University Joseph Fourier in Grenoble, France. She joined the European Synchrotron Radiation Facility in 1993. At the ESRF, her scientific career evolved around the development of synchrotron methods to probe local and electronic structure, and the study of correlation between magnetism and the structure in compressed matter under extreme conditions using X-ray absorption spectroscopy and X-ray magnetic linear and circular dichroism. From 1997 to 2019, for more than 20 years, Sakura was in various scientific leadership positions at ESRF. She was in charge of X-ray spectroscopy beamline ID24 and BM23. She was head of electronic structure and the magnetism group and head of the matter at extremes group. In September 2019, Sakura joined the European X-ray free electron laser facility at Hamburg, Germany, as scientific director responsible for development of the scientific program in the 4 short-wave hard X-ray instruments. Sakura was also has been an active member of our high-pressure community. She served as secretary of the Europe, was elected as vice president of the Europe in 2019, and will be the chair for 2022 high-pressure Gordon Conference, Gordon Research Conference. Today, she is to present new scientific opportunities for study of matter at extreme conditions at the European XFEL. Let's welcome Sakura. Sakura, please take it over when you're ready.
Thank you, Yumeng. So thanks for inviting me to this high pressure special interest group. I finally made it here. Zulu asked me 2 years ago and we finally found a date. So I'm glad. And yes, I'll be telling you about this new facility. So I don't know how many of you are familiar with free electron lasers. So I have prepared a few slides at the beginning. And then I will talk about the facility in Hamburg, show you a few examples of first scientific results in other fields that are not extreme conditions. And then the second half of the talk will really be focused on the status of this high energy density instrument. So I'm sure that many of you are aware that in the past decade or so, there have been very important developments in the field of accelerator-based X-ray user facilities. So on one hand, we see here the advent of the multiband achromat storage rings, which are sort of revolutionizing synchrotron radiation, with much smaller emittances and much higher brilliances. So we started with Max 4 in the soft X-ray regime in Sweden. Now we have ESRF that has just started operation. This was the first of the hard X-ray synchrotrons to undergo this change in the lattice. And I heard that APS is coming up next in about 2 years. On the right, we have seen, let's say in the past 10 years, the advent of hard X-ray free electron lasers. And so this started with LCLS in 2009. This was the first hard X-ray free electron laser to become operational. And then there's been a few more, one in Japan, Sakura, one in Korea, PALFEL. Then there was one in Switzerland, SwissFEL, and the European XFEL in Germany. And so among these, the European XFEL is the only one, the first actually, that is powered by superconducting cavities. And this allows it to reach much higher repetition rates. So in talking about X-ray free electron lasers, I like to show this slide, which really places these new facilities in a much larger context of these high brilliance light sources. So we have on one side the synchrotrons that many of you know very well. So these are very, let's say, high performance sources, X-ray sources. You have electrons that circulate in a ring, and they, provide X-rays to many, many groups that work at the same time. So that's why they're very efficient and they're very stable. And in the past 50 years, we have been developing at these synchrotrons all sorts of X-ray based methods to study matter in all sorts of forms, including at extreme conditions. Then we have here on the right, the laser radiation facilities. So these are, well, actually, there are all sorts of kinds of lasers, from off-the-shelf lasers to home-built lasers that you work on in your university lab, to high-power facilities, high-intensity laser facilities as well. This is a huge community, and it has really been developing ultra-fast science with these very short femtosecond pulse lasers, really high intensity, so ultra-fast methods and also non-linear methods. And then in the center, you have the X-ray free electron lasers. And this is, light sources that fall a little bit in between these two. So they are X-ray sources characterized by very high peak brightness. They're pretty coherent, not as much as lasers, but very, very high spatial coherence. They're single pass, so they're not very efficient in the sense that they can serve one instrument or a few instruments. So they're far from, the efficiency of synchrotrons. And they're these are pretty new facilities. So there's not many worldwide. And up to now, as I was mentioning at the beginning, we're still sort of learning how to really exploit this radiation. So we're copying a little bit from the left, the X-ray methods, we're copying a little bit from the right, to do ultra fast science, because here we have very short pulses as well. But as I said, it's going to still take years before we really learn how to exploit all the properties of this unique radiation, which actually is pretty different from synchrotron radiation. And so here, I really want to highlight these differences. So here on the right, you see that the pulse length is much shorter. It's of the order of tens of femtoseconds at XFELs, compared to typically 100 picosecond of duration of pulses at a synchrotron. Then also the number of photons per pulse is much higher, is orders of magnitude larger. So these are really, really intense. Then here on the left, you see the distribution in energy of the pulses and in space, which is very inhomogeneous. So this is very different from what you have at a synchrotron, where you have very smooth, energy dependence of these undulator harmonics and very smooth spatial dependence of the photons, spatial distribution. And finally, you can see from here that you have very strong instabilities, pulse-to-pulse instabilities. And this is because of the way these pulses are created. So they originate from a stochastic process, the so-called SASE process, which stands for self-amplified spontaneous emission. So these X-ray free electron lasers are characterized by extremely short pulses, femtosecond pulses. And so now, we can start doing all the ultra fast science that up to now has been really the domain of lasers, except that now we have X-ray wavelengths. So we are sensitive to atomic positions. Also, we have chemical selectivity, because we can tune the energies of these photons to specific absorption edges, and we can select, specific atoms in complex systems. And we also have bulk sensitivity, because these hard X-rays penetrate. And so these facilities have changed the way we probe matter with X-rays, because we have atomic resolution and we can follow atomic movement on the relevant time scales. And also, they've changed the way we approach structural determination with X-rays, because I don't know if many of you know this paper. This was 20 years ago, a paper this was a theoretical simulation showing that you could actually concentrate a huge dose of X-rays in a very short pulse, a few femtoseconds, and this would allow you to obtain structural information from a molecule, for example, with atomic resolution before the molecule actually is damaged by this huge dose. And this prediction has actually been verified, experimentally verified. So this is how we work today. So we can look at extremely radiation sensitive samples, tiny crystals. We can look at proteins or biomolecules in their native environment, so at ambient temperature, so they can move, you know, they're in water. We can see how they move. We can use pump and probe methods to actually follow the structural changes as these proteins do their biochemical processes. So all this is new, and this is something that is really starting now with these facilities. So just to summarize, the new opportunities offered by X-ray free electron lasers. So we have the ultra short pulses that allow us to do structural dynamics, but this time now with atomic resolution. We have the coherence of this beam, as I said, almost full transverse coherence and very high temporal coherence, which obviously boosts all the coherent imaging methods. And finally, the very high intensity of these pulses, which allows us to start looking at nonlinear processes, again, with atomic resolution. So the open science problems, so very quickly going through them. So we've seen the biomolecules and proteins and see how, for example, their structure is related to the function, because we can see them move when they do their function now. Chemistry, biochemical processes, we can start looking at how these evolve in time and how these bonds break, how they form. In solids, we can excite, for example, coherent phenomena, coherent motions like phonons. We can photo-excite these, and then we can see, for example, how how the electron energy bands change, synchronized to these coherent modes. And then we can learn about electron-phonon coupling, for example. And finally, we can study extreme states of matter that are produced, for example, in shock compression and are very short-lived. And so we can use these very short pulses to study matter at extremely high pressures and temperatures. Okay, so now a few words about our facility. So the European XFEL is an international user facility. It is funded by 12 shareholder countries, mainly by Germany and Russia. So the company, the European XFEL company, has constructed and operates the X-ray laser. And our partner institute, DAISY, has constructed and operates the accelerator. The construction started in 2009 and the start of operation in the middle of 2017. And we have both soft and hard X-ray instruments. So this is a photograph seen from the top. So here on the bottom right, we have Hamburg. And then here, those of you who know DAISY, you can see the DAISY campus with the Petra ring here. And our electron injector is right here at the campus. The whole infrastructure is underground, so everything is in tunnels. So these electrons are injected into this long tunnel, linear accelerator, which is about 2 kilometers long. And at the end of the accelerator, they reach a maximum energy of about 17.5 GeV. And as I said, you see here a picture of the accelerator. This was the first high energy X-ray free electron laser powered by superconducting cavities. And so the fact that they're superconducting allows you to go to very, very high repetition rates and to reach about more than 2 orders of magnitude more photon pulses per second on the sample. So here the electrons are injected into different tunnels where they interact with very, very long undulators, hundreds of meters of undulators. And then the photons are used in a very large experimental hall, which is underneath this administration building. And here we are about 3.5 kilometers from DAISY. So I want to say a few words about the distribution of the beam of these electron pulses, electron bunches. This is the end of the linear accelerator, and this is where they are injected into these different tunnels. So at the moment, today we have 3 undulators. We have 2 hard X-ray undulators covering approximately the energy range between 5 and 25. SASE 1 and SASE 2. And then we have 1 soft X-ray undulator that covers roughly the range between Today it's 0.53, but very soon it will be 0.3 to 3 keV. Now, each of these undulators can provide photons to 2 independent instruments. So at the moment we have 6 instruments, of which 4 are in the hard X-ray regime and 2 in the soft. So here, this is a table which summarizes the key parameters, and I've talked about most of them. I want to focus a little bit on the distribution of these pulses, because this is really specific to the European XFEL. So the radio frequency of our accelerator runs at 10 Hertz. So this means that every 100 millisecond, it produces a big pulse, what we call a macro pulse. Now, inside this macro pulse, we can fit up to 2,700 electron bunches at a minimum spacing of 200 nanoseconds. So in practice, we work in a burst mode. So these are bursts of electron bunches. And within the burst, you can reach a repetition rate of up to 4.5 megahertz, which corresponds to this 200 nanoseconds. Now, each of these trains can provide photons to 3 instruments. So to the 3 instruments. So we can actually, in this sense, run 3 instruments simultaneously. So at the moment, we have the 6 instruments that are all in user operation. They started at different times, and the last ones to open were the SASE-2 instruments, MID and HED. So HED was among the last ones to accept users in 2019. And then in the first months of 2020, we all fell into the Corona restrictions, and so we had to close the facility. And HED had a hard time because many of the systems had not been fully commissioned. So we're just picking up things now. Things are gradually going back to normal now. So here I have made a collage of the first publications that are coming out, and I have picked a few which I will go a little bit more in detail. I just want to highlight the fact that many of these first publications, look, the titles, they all start with megahertz. There is this megahertz a little bit everywhere. And the reason is that this was really the novelty here. I mean, and this was a huge challenge, and we're still struggling with this megahertz repetition rate. So everything is difficult. I mean, every aspect of the experiment has to be compatible with this megahertz repetition rate. So from sample preparation to sample delivery, to the detectors, to the data pipelines. For example, for the biology community, they struggled with these jets, and they had to develop special jets, which were, really thin and really fast, so that, the pulses coming in at 200 nanoseconds would not perturb the next measurement point. So that was a lot of work. So I've picked here a few examples. So the megahertz repetition rate was used to do megahertz microscopy. And so here, this enables us to follow very, very fast processes that evolve, at speeds of the order of kilometers per second, and to make movies with images of, micron resolution. So this kind of application can be very interesting, for industry, also for industry, especially if we can develop, megahertz projection tomography, that is, 3-dimensional movies. And this is something we're working on now. So this paper showed this first experiment, which where we, let's say, have a laser that exposes a water-filled capillary. And you can follow, with micron precision, the shape, the direction, the size, velocities of all these little water and glass particles that are formed. And then you can compare this to models based on our actual understanding. And we see often that these models just are not able to describe what we see, which tells us that, that it is really important that we start doing these experiments. This is another nice experiment where we were looking at these strongly driven cavitation events. And these are very, very interesting. They exhibit a lot of non-equilibrium physics. So these things, they explode, they create pressure waves, they do chemistry. A lot of interesting things happen. So what they did here is they generate a cavitation event using an optical laser pulse. In this experiment, this was a nanosecond laser, but this week they repeated this experiment using femtosecond lasers. And they were able to see many more things. But anyway, what they do here is they generate this cavitation event for example, this was a cuvette filled with water, and then they image this bubble with a single X-ray pulse. And they image this using imaging detector, as you can see here, and then you can change the pump probe delay, and you can follow the formation of this bubble all the way from the plasma spark until it collapses. So you see, with X-rays, you have access to the phase of this image. And so you can see inside the bubble, and you can, from this phase, you can get the pressure distribution in space and in time. And this is something that you cannot get with optical imaging. And so then you can compare, the pressure distribution from inside to outside the bubble. You can compare these this time and space distribution with models. And again, here we notice that the models are not really able to reproduce what we measure. Okay, this is the last example that I took from the soft X-ray instruments. So here they use the very high intensity of these pulses to look at nonlinear processes. And these are typically very difficult to visualize and to study because they're usually, covered by the much stronger linear signals. And so this group developed a method which is based on a photon recoil imaging. So these are images on a detector. And with these images, you nicely see the signature of the nonlinear process on top of the background of the linear process. So I'll explain to you how they did this. What they did is they used a neon atomic beam of neon atoms, and they had X-ray pulses interact with these neon atoms. And then they placed this detector behind the interaction region. So after the interaction, you have the formation of these neutral neon atoms that just propagate, and they end up in some position on the detector. Now, the energy of the pulses is chosen so to excite the 1s neon electron to the 3p state. And then you have a bunch of excited neon atoms here, and they want to de-excite. And they can do this in two ways. Either through the spontaneous emission, which is this wiggly blue line. And this is the linear process that we know. This is fluorescence. And we know that these photons go all over the place. They are emitted isotropically. So when this happens, this neutral neon atom that propagates all the way and hits the detector receives a little recoil, a little kick in all directions, because the photon goes off in all directions. And that's this image here. They're distributed over a large area. However, this de-excitation can also happen through a nonlinear process whereby the atom actually absorbs two photons simultaneously. These two photons come from the same pulse, and they're traveling in the same direction. So when this second photon causes the de-excitation, there is no recoil. And so this neutral neon atom just propagates straight from this little segment here, interaction region, all the way to the detector. And you can see it here. You can see this little segment. So that's the way that they distinguish these two. And this is a very elegant way of doing it. And this is important because very soon we will be able to control two photons. We will be able to control their energy, so choose their energy, and also control their time delay with the femtosecond precision. And when we are going to be able to do that, then we can excite. For example, we're going to be able to decide what to excite, what atom, what electronic transition, and that's where we're going to be able to follow electrons and see how they move from one atom to the other. So all this is really, really, exciting for what comes next. Okay, so now I'll talk about the second half of this talk about the high energy density instrument. Starting from this summary slide of the properties of the X-rays on this instrument. So this is a SASE-2 hard X-ray undulator. The energies are roughly between 5 and 25 keV. The duration of the pulse is a few tens of femtoseconds. photons per pulse. At 5 keV, there's about 10 to the 13 photons in this pulse. The spot size on the sample can be tailored depending on what you need with different sets of lenses. It can go down to a few hundreds of nanometers. Also, the bandwidth can be tailored. So we have a monochromatic beam. We also now have seeded beam. So this is very recent, but it works nicely. Or you can use the SASE beam. So here you have a few tens of EV bandwidth. And then HED really uses the whole possibilities of repetition rates that we have at XFEL, from the single pulse, so shot on demand, to the full burst. And I'll show you some examples there. So here I'm showing the energy per pulse in millijoules as a function of photon energy. So you see these pulses are pretty energetic. They're typically a few millijoules each. And they also, let's say, scale with the energy of the electrons. So when we work at high electron energies, this is the accelerator energy, these photon pulses are more energetic. So this is the structure, the time structure. As I said, HED often uses this this burst, and they play on the repetition rate within the burst to access different time scales. So they can look at different dynamics. Okay, so HED, they do practically, they focus on research on matter at extreme conditions of pressure, temperature, magnetic fields. They have different drivers. So a big activity is to look at matter at very, very high densities and temperatures. Let's say limited to a few thousands of Kelvin, so below a few electron volts. And these are typically the conditions you find in the interior of planets. And these states can be prepared using either long pulse lasers, nanosecond lasers, or even the diamond anvil cells, laser heated, or heated with the X-ray pulses as well. You can also, so HED also studies states of matter that are close to solid density, but extremely high temperatures, up to several kilo electron volts. And these states can be reached using ultra intense laser pulses, so high intensity lasers, or the X-ray beam itself, again, because these are femtosecond pulses and they're extremely energetic. And finally, HED also develops a whole bunch of different methods, or they work on instrumentation. They also work on different kinds of sample environment. Okay, so this is a list of drivers that are either already available at HED or that are planned. As you can see, many of these are financed by this HIBEF consortium, which is a consortium of different institutes led by HZDR in Germany, but also DAISY and STFC and many others. So they have financed the diamond anvil cell platform, which is now operational, actually since the end of 2019. They also financed some of the optical lasers, and I'll say a little bit more about these later. They also financed a pulsed magnetic field coil that is not ready yet and will be probably available in 2023. And finally, HED is also working on an X-ray split delay line that will allow to do X-ray pump, X-ray probe experiments. And this is probably going to be ready by the end of next year. So this is a sketch of the instrument. So the X-rays come from the left. So the SASE undulator is hundreds of meters upstream. Here we have the optics hatch that I took out of the drawing because there were too many things, so that you can see this laser. This is the pump probe laser provided by the facility. It runs at the megahertz, and all the instruments have one of these. Then we have here the experimental hatch on the bottom with two big interaction chambers, IC1 and IC2. And on the top, we have the two big lasers. So here we have the high intensity laser. This is 25 femtoseconds, 300 terawatts running at 5 hertz, or 100 terawatts running at 10 hertz. And here we have the dipole laser. So this is a 100 joule laser, 10 nanoseconds running at 10 hertz. The pulse is has a pulse width that can be varied between 2 and 15 nanoseconds, and it can also be frequency doubled. So this laser here was delivered at the end of 2019. It comes from the UK, from STFC. It made it just in time before Brexit, so just before Christmas 2019. And unfortunately, then we had the restrictions that stopped travel from UK. And so a lot of the commissioning that we had to do off beam was just delayed because travel was not possible from the UK. So this laser is delayed. It's not going to be available for users probably until the second half of 22, although there is probably a user-assisted commissioning in the first half of 22. This one has been commissioned and is now is in user operation, and this one as well. This is a photograph of inside the hutch. So the X-rays come from the left. You have here the first interaction chamber and the second one. The first one is very big, and it's big because it has a lot of diagnostics inside. It has spectrometers for emission spectroscopy, for inelastic scattering. It also can receive the two big lasers from the top, the high intensity and the high energy laser. And this second chamber is smaller. It's really dedicated to the diamond anvil cell platform, but it can also receive the long pulse, a high energy laser to look at a shock on pre-compressed samples. And see, these chambers are on rails. You can put them in and out, and the pulse magnetic field facility will be here, and you will be able to push it in and out instead of this one. And then you have behind, you have a series of detectors that can also be pushed in and out on other rails. So I'm going to show you a little bit of a few slides on how we get to these extreme conditions and different methods. So we have diamond anvil cells that allow to compress a sample very slowly to several megabars, and this maximum pressure will depend on the size and the shape of these diamonds. Then we can either oscillate pressure using piezo actuators and have access to dynamics on the millisecond time scale, or we can laser heat using pulse lasers, the sample in the diamond anvil cell. And here we are looking at dynamics in the order of a few nanoseconds. And then we can use our burst mode to study, follow the structure and the electronic structure of whatever we have in the cell on these time scales. Then we can use the long pulse laser to shock compress the sample, either with one shock, with two shocks, with three shocks. We can access different areas, the different zone of the temperature density phase diagram. And we can also shape this pulse to approach the isentrope, for example. Or we can isochorically heat a sample very, very rapidly using these ultra short optical lasers, the high intensity laser, or the X-ray beam itself, which is also a few femtoseconds. And in this way, we can access, extremely hot states and study out of local thermal equilibrium physics here. Or finally, we can isobarically heat a sample by exploiting the burst mode. So here we heat a sample with successive pulses throughout the burst. We can heat them up to melting, for example. We can see phase transitions. We can see chemical reactions that are induced by temperature, for example. And we can play on the dynamics by changing the delay time between each pulse. Okay, so this is the first experiment one of the first experiments that we did on HED. This was in the autumn of 2019, so I had just arrived. And this experiment really dealt with trying to see whether we could couple diamond anvil cells to these ultra intense X-ray free electron laser pulses. And I remember many years ago when we were discussing this in the community, and we all were convinced that we would never be able to do these experiments because we were sure that these pulses were going to blow up the diamonds. And so there was a lot of preparation work. This was a huge community proposal with 70 participants and 50 or 60 diamond anvil cells. And people did a lot of simulations to try to understand, how heat is transferred from the sample to the medium, from the medium to the diamonds, and so on and so forth. And it turns out that these experiments really work very well if you prepare your sample correctly. And only one of the cells was actually destroyed by the beam in this experiment. This is one of the first papers that came out from this community proposal. And it shows ultra-fast chemical synthesis of an iron nitride at high pressure. These experiments are actually very interesting because you see how you can use the activation energy in these pulses to trigger chemistry at high pressures, and you can exploit the separation between these pulses in the burst to look at different time scales. So in this experiment, they had an iron foil, which was loaded with nitrogen gas in a diamond anvil cell and was compressed to 5 GPa, and it was exposed to 2 pulses. Here you see a simulation showing how the temperature on the sample and in the diamond increases throughout the burst. Now, in this case, after the second pulse, the temperature went beyond 1,400 Kelvin. And we know this because we saw the transformation of alpha iron to gamma iron. And so then they were able to follow, the dynamics of this chemical transformation. And they were able to look at the sample post-mortem using FIB, and they saw that this chemical reaction actually happened simultaneously across the whole bulk of the sample. This is an experiment using the pump probe laser, which is relatively weak. I mean, it's 50 millijoules per centimeter squared. But the aim here was really to study the effect of pre-pulses on pristine surfaces. So pre-pulses always happen when you do terawatt laser experiments. And these pre-pulses destroy your surface, and there is a reconstruction. And the aim of this experiment was really to study these phenomena. And so here they used grazing incidence small angle scattering. So they could play on this angle to increase sensitivity to the topmost layers, let's say hundreds of nanometers. And they were able to observe very, very rapid, let's say, destruction of this surface, and followed by a major reconfiguration. So this is really important to understand how these things occur and what kind of surface you have when you have the big terawatt pulse that arrives. And this is the commissioning of the relapse laser. So this was very, very difficult and took much longer than expected. As you can imagine, when you come in with a terawatt, 300 terawatts on a sample, you generate a whole bunch of particles, very energetic particles that go all over the place, and a lot of bremsstrahlung, very energetic bremsstrahlung radiation. And all this has to be correctly screened. Otherwise, you just can't see any signal. It's just background. And so in August 2020, we finally saw a first real small angle scattering signal from a tungsten wire that had been hit by the relapse laser and then probed by an X-ray pulse 750 femtosecond after the laser. Now, this was possible only because we added a whole brick wall, a lead brick wall, to screen all this radiation. We also put a HAPG crystal to deviate small angle scattering signal off the direction of the bremsstrahlung. So this is what the setup looks like inside that big chamber. So here you see the X-rays coming from the left. This is the pink beam. This is the sample holder, which is a target holder. This is a standard target holder developed in this UCOL European project, which holds something like 100 targets. This is the famous lead wall that I was talking to you about, with a little hole. this is the crystal, the HAPG crystal that deviates the small angle scattering signal into a detector, which is outside of the chamber. And in this crystal, there's also a little hole that allows for the transmitted beam to go through and to hit an imaging detector to measure phase contrast imaging at the same time. So this setup allows you to measure at the same time small angle scattering and phase contrast imaging. And this is the terawatt laser that comes from the top into the chamber and then is focused with this last lens onto the sample. And this is a photograph of inside that big chamber. So the X-rays come from the left. This is the target holder, which has about 100 targets on it. This is the brick wall, the lead brick wall with the hole. And this is the big lens, that the last focusing lens of the high intensity laser that focuses the laser on the target. Okay, and here I'm showing data that was taken a few weeks ago. This was preparation for a user experiment. And here they were studying hole boring on a 10 micron diameter copper wire. So on the top you have the cold and the pumped small angle scattering signals, and on the bottom you have the phase contrast imaging measured at the same time. So the data here is with 0 time delay between the X-rays and the laser. So you can see here, this is the shadow of the 10 micron copper wire that is still, unperturbed. And here you start seeing after 1 picosecond that it is sort of changing shape here. And then after 20 picosecond, there is no more wire. It's gone and there's a big hole. So they're looking now at the data in between these two images to try to understand how this occurs. Okay, so now I'm showing here, let's say 2 dream experiments. So many years ago when HED was conceived, they had to write a science case. And in this science case, they described 2 extremely challenging experiments that may be possible in HED. And this implies creating extremely high purity states of polarization for this XFEL beam. And, XFEL beams have a much smaller emittance and therefore smaller divergence than synchrotrons. So in principle, you would be able to reach higher polarization states at XFELs. So what do they want to measure here? So here they're interested in measuring these ultra high magnetic fields that are expected to be generated when you hit a solid with a very intense laser, femtosecond laser. So what happens here, you have very fast charges that are accelerated in this direction, and they generate these very high magnetic fields. And you would be able to measure these magnetic fields by measuring the change in polarization of incident X-rays. And so that's what they want to measure. And here, again, you use highly polarized X-rays and you try to see tiny changes in the polarization state after transiting through a region where you had vacuum, and you hit this vacuum with a high intensity laser, and the electromagnetic field is so intense that you start creating electron positron pairs, and this polarizes vacuum. You have birefringence in this region, and this would be detected by a slight rotation of the polarization of your X-rays. So I don't know whether these will ever be possible, but anyway, these were in the science case and we are working on this. So now I'd like to close this seminar just telling you a little bit about our strategy. So we're working now on the strategy for the coming decade. And one of our strategic goals is to widen and diversify our user community, because our user community is actually quite small. I mean, I come from a synchrotron. I've worked almost 30 years at a synchrotron. And I can see the difference. I see very often the same names in these proposals. And so this is something that has to change. This is really important for the sustainability of these facilities. So we're trying to make these experiments simpler so that we can have smaller groups come and use them, a little bit like synchrotrons. We're also focusing on training, supporting new users. We're encouraging, for example, new groups to work with expert groups through these community proposals, for example. We're also encouraging our staff to establish collaborations with shared students, with new user groups. And we're also implementing new access schemes so that this may be easier for some groups to get beam time. And so for the future, I can say that this is a very young facility. I mean, we still have to figure out how we're gonna run it and how we're gonna exploit these X-rays really. So we have, what I can say is that the coupling of hard X-rays with megahertz repetition rates is really challenging. It's difficult, these experiments are difficult, and we're still struggling with, with all this data, these detectors, the optics, the heat load. But I think that, this coupling is opening new perspectives. And much of the potential of the facility is still to be exploited. So we still have to complete instruments. We still really have to start looking into this nonlinear phenomena. We've done very little there. We're going to be coupling more to ultra-fast sources of all kinds, but we're very far from having a complete set. We're working on special modes. As I said, self-seeding is already available on some of the instruments. We have 2-color on the soft X-ray instruments, and this is going to be available also for the hard. And we're also working to get this pulse shorter. And finally, we're thinking about going towards harder X-rays in the next decade or so, using superconducting undulators. And for this community, you might be interested in a workshop that we're organizing at the beginning of spring 22, where we will be discussing with the community scientific opportunities with very hard X-ray free electron laser radiation. And by very hard, it's much harder than what we have today. So this is something of the order of 40, 50, 60 keV. So we want to see whether there are some scientific opportunities there or not. And so I'd like to acknowledge many, many people, in particular the staff at HED. They were, especially the people listed here that helped me put together all these slides. And I also want to thank all the user groups, and there were so many that I just couldn't fit their logos on this slide. So I just thank all of them. And with this, I'd like to thank you for your attention.
Okay, thank you, Sakura, for the exciting presentation. And most audience here are diamond aerosol people, and I'm sure there will be questions related to diamond aerosol experiment. So let's go to start the Q&A session. Vitali, please take over.
Yeah, thanks, Sakura. It was great overview of everything that in future possible at XFEL. It's definitely more stuff you can do there than with storage ring, but some of the important things that we you may complement when we study at storage ring, and then we implement ready experiment at XFEL. So it's will kind of like more efficient way to do.
Of course.
Yeah. So audience, if you have any questions, you can raise a hand. Just type in chat questions that you want to ask. Before I will ask you, I have a few questions. You was talking about the imaging. It was very interesting. Is there any steps you are doing for imaging in diamond anvil cell? Like,
well, this is a difficult question. I mean, I don't know. I think that there will be, at the moment, we don't have any thing ready. At the moment, the diamond anvil cell platform has diffraction available, megahertz diffraction, as I showed you. Actually, that experiment that we did in 2019 didn't even have a megahertz detector. It wasn't even ready. So we used a 10 hertz detector, and the images that you saw were just collected one on top of the other, because we did not have the possibility to read every single pulse separately. So, but we could see the peak move, and that was enough, to get the information. But now we do have a megahertz resolved detector there. It's not the final one, but we have found a solution. So we have that detector. We can also do emission spectroscopy in the diamond anvil cell, and also in elastic scattering, although we did not yet do an elastic scattering, but that is also possible in the other chamber. We have not done any imaging yet. So
yeah, it would be interesting if you can do like correlation spectroscopy and see when the sample is melting and see there, because you have coherent beam. That's what we don't
I
have
know,
yet.
I know, of course, it would be really interesting. I think that it's not too complicated because we can put an imaging detector behind.
Yeah.
Um,
Yeah, it just need to be very fast. And you didn't talk about the detectors at all. I was surprised. I was thinking you'll say, okay, now we have that detector and everything will be different.
No, I didn't talk about detectors. I thought you were more interested in, seeing the science.
Yeah.
I mean, I'm not a detector expert. I mean, I don't know what you want to know about detectors. Maybe I can answer your questions. I mean,
just like what the level right now, it's like a first kind of like detectors. They will use it like in a couple of weeks. But is there any other behind that to develop larger detector, or because right now it's small?
Yeah, so first of all, I want to say that the detectors that were planned for this facility, some of them are not here yet. So we're still waiting. For example, HED, they're still waiting for their real detector. This is a 1 megapixel AGIP detector. They don't have it yet. And then other instruments also don't have their detector yet. It's just that it's difficult and these things are complicated. We found a lot of things that didn't work, but we're fixing them. So it's getting better. Now, we do have limitations. So let's say the AGIP detector is the most used diffraction detector. It runs at the megahertz. So it, it takes every pulse every 200 nanoseconds and it stores the charge and then it reads out because we have 99 milliseconds with nothing happening. And so we can read out. So that's good. But the problem with this AGIP detector is that the pixels are very large. They're 200 microns. So you cannot really use the AGIP for imaging. So we don't, to answer your question, we don't have an imaging detector that can run at 4.5 megahertz, or at least not the AGIP, with the properties of the AGIP. So we have, for example, we're using detectors that we were using at the synchrotron, the imaging detectors that can run at megahertz. Those we use them.
Okay.
But the AGIP, the advantage of the AGIP is that it has an adaptive gain, so it can adapt depending on how intense the beam is, and so that's great.
Yeah, if you can reduce the pixel size for Egypt, it will be very great.
But this is not going to happen. I think it's going to take years, maybe even a decade.
It's fine. We have a lot of students. They will be waiting.
Another problem of the AGIP, since you got me on the detectors now, I'll tell you all I know about the detectors. Another problem we have is that they are made of silicon. And we are now working more and more at 18, 20, 25. And that's becoming a little bit tough.
Yeah.
So the other thing is
the materials will be better.
With gallium arsenide or something like that, or zinc, tellurium, or one of these things.
Yeah. Okay, and you also mentioned about efficiency working at the XFEL facilities. We do have successful a few community proposals. And what do you think now? It's probably will make sense to go to single user proposals. What do you think that you will make like a standard setup? And because one group, two groups cannot prepare many diamond cell, like 56 is that required for 2 days of running experiment. Do you think that you can have like a standard setup and have like 4 hours for one group and then switch to another?
Yes, we are doing exactly that. I mean, in our vision, the European XFEL has to be an XFEL which is open to anybody that wants to come and do an experiment, not only the,
super
groups with plenty of money and 40 people that can come and, no, we don't want that. I mean, we have those groups, which is great, and we're very happy, but we cannot live just with these groups, right? Because we have some countries that don't have these groups. And these countries are funding the European XFEL. We absolutely have to get those countries in. And those countries only have poor universities, like Italy. I mean, we don't have very rich groups which can come with 40 students. So we're working hard on that, but we are already now in this call 8, we're opening standard configurations for MID, HED, and FXE. And so you go on the website, you click standard configuration, and it explains to you what is the standard configuration for that semester. It can change, right, semester by semester. And then you try to make your experiment fit. And if it does, you have more chances of getting beam time. And for us, it's much simpler.
Yeah. And will you provide some support in terms of equipment, travel funds, or?
Well, I think that if you have your proposal accepted, you have your trip paid and your guest house paid. I don't know exactly how many people, but it's quite a large number of people. Mm-hmm. And we are trying to especially help the small shareholders and the underrepresented shareholders. In our facility, the most prominent underrepresented shareholder is Russia, because Russia pays, I don't know, did you see almost 1/3 of the budget?
Yeah.
And they need to get something out of this facility. And so we are helping Russia by funding, students or even sabbaticals. Not only Russia, even other countries like Hungary and Poland, they also don't have big groups, right? And they are funding this facility. So
sounds good. I just want you to announce that, because some people think that it's very hard to get the beam time, but when you have a standard setup, probably it will be much easier to get in and get the results we want.
Yeah, exactly. Our goal, maybe it's not going to be immediately reached, but our goal is to have smaller groups come, and then they find at the facility what is needed. They don't have to start fiddling and create their experiment from scratch. It's there. They just have to bring their sample. And we will try also to help them to analyze the data, because you can imagine how much data these things are producing.
I know, don't tell me, I know.
It's crazy. So if you're not an expert, you're completely lost. You don't know even where to start. You don't even know how to take the data home. That's the first problem, take the data home.
Yeah, it's all large facility facing this problem, but we can solve that. There are some solutions. Okay, great. Yeah, it's a huge opportunities, and I think our audience glad to hear that. And I don't see any more questions from audience, so back to you.
Okay, just a quick question: that what's the typical beam size you can focus to for diamond nanocell work?
Well, on HED, I think the minimum is something like 300 nanometers.
Oh wow!
But there are some issue with stability.
And you mentioned
that we have still a lot of issues with stability.
Okay, so you mentioned that you need a lot of diamond nanocells prepared for experiment. Is that means the time for each deck usually going really fast? I mean, you know what it's like with synchrotron. It takes a couple of hours for one deck.
Yeah, well, I mean, if you're looking at an irreversible chemical reaction, like the one I showed, that's over in a burst. So that's a few microseconds and it's done. Then you can go to the next one. I mean, it takes, you work with you have a burst, you use it for that cell, and then you change cell and you do another one. And I mean, it depends on of experiment.
It's in a vacuum, and usually what we're using is revolver, so it has a few DAGs simultaneously. We want to use every second of the beam time, so that's why it's very important.
Maybe we have to develop better exchangers for diamond nanocells. Maybe we can fit more in there.
Yeah, small like mini BX90, it will be perfect. So it's made
exactly. This is stuff that can be done, and yeah, we're really keen in making this a very standard place. Of course, it's not going to be just standard experiments. We're going to keep a big chunk of the beam time to do new things and, exploratory stuff. And this is normal. We have to do that. But at the same time, we really want to make sure that we have some simpler things where we can, foster a real community. Yeah.
Yeah, absolutely. Okay, well, thank you so much. I know it's late there, and you haven't eaten dinner yet, so thank you so much. We really appreciate it. And
you're welcome.
Okay, so next presentation in November 15th will be Vitali. Ta-da! And so he is going to talk about polymorphism of superionic ice. So we're looking forward to it.
Yeah, it
And,
will be very interesting. Everyone come and bring your friends.
Okay, 25th of November or
no,
15th.
November 15th.
on November 15th.
Yeah, yeah. So,
I have
and
this-
we'll take a break in December and for holidays, and then we will restart in January. All right. Thank
Okay.
you everyone for coming.
Thank you, Sakura, again.
Yeah.
Thanks to you. Thanks for inviting me. It was nice to be here with you.
Yeah, it was great.
For
Thank you.
real.
Yeah, and you see a lot of applause, you see on the screen.
Yeah, I see that. Great. See you
See you
soon.
guys next time.
Bye-bye. See you.
Bye-bye.